guys, I missed you so much. Hope you did well on your test on polar graphs and polar coordinates. I've seen a few go up so far, but it just opened, so I haven't seen all of them yet. But this is your introduction to limits, and if you have your textbook with you, which I know you guys don't, if you have your textbook with you, it is chapter 12. We are going to spend the next just about 4 weeks. So the rest of this week, the next 3 weeks, and then part of the fourth week on this unit. And depending on what happens with school and whether or not we go back to school on May 4th or not, then we will be back face-to-face to finish this unit. If not, then we'll finish it online. And then we'll just obviously every day is a new experience. So I'm going to start, not by doing that, by doing this. And I'm going to put your notes into OneNote already. That way you can, have them in your notebook. So pretty cool. All right, so this is Introduction to Limits with Tables and Graphs. Sorry, I put it under the Limits tab. You can see here, and then it's in section 12.1. So it's the Introduction to Limits using tables and graphs. So if you are taking calculus next year, this is the very first thing that me or Mr. Swan, will do in calculus is to go over how to take limits with tables and graphs. I'm gonna need to pause this for a second because this isn't working. Hold on. Okay, sorry. So first of all, I need you to understand that the idea of a limit is not about what happens once you get there. So first of all, we've got this limit concept, and a limit is about movement. It's about what is happening to a graph or a curve as you are approaching somewhere. It's a movement as you approach a value. So think of like, doesn't matter what's happening at that value, it doesn't matter what's happening at that moment. So like right now with us in this, Corona, COVID, quarantined, isolation, social distancing phase that we're in, it doesn't matter what's happening right now. We are focused on, this is what I'm trying to tell myself anyway, we are focused on getting out of this and getting back to normalcy. So we're trying to hopefully head in the direction of back to where we once were, and that's our limit. We are heading towards normalcy. So let's take an example of something like, a function, let's say that we're looking at a parabola. Or let's even just take a line. Let's take a function like, say, 3x minus 2. So if I were in Algebra 1, or if I were, wherever you are, which is pre-calc, obviously, and I were to graph this line, it would, of course, look something like this, with a y-intercept of -2 and a slope of 3. If I were to have asked you a question about the limit, in words, I could say, what is the limit of the function, we'll call it, just say f of x. So what is the limit of f of x as x approaches, sorry, you could spell, as x approaches x equals 0. We'll just say that, for example. So that's a lot of words and a lot of things to write. So mathematicians are smart and they say, you know what, we need some symbols to represent these words. So what they would do is they would use just LIM. And I always put it in cursive because I don't want to think that I'm looking at a variable or something, so I always write it in cursive. It's just my habit. So this says, what is the limit of, so that of means that there's something plugged into that, function, quote unquote, kind of like sine of pi over 3. I would have to put the pi over 3 into the sine function. I wouldn't just write sine equals, I would have to say sine of pi over 3 equals, and then we could say the square root of 3 over 2. This is the same thing, the limit of the function that I'm looking at. So I can either put in f of x here, or I could write the limit again of my function, which is 3x minus 2. So either one of these is fine. As x approaches 0, as x approaches x equals 0. So that goes right below the limit. So you put a little x with an arrow, 0. Now, you remember when I talked about, hopefully you remember when I talked about end behavior. So I'm going to take you back for a second, take you way back to beginning of the year, when I would say end behavior for functions. So we were talking about like a polynomial. Let's say we had something like this. Okay, so, and I would say the end behavior, well, the end behavior was as x approaches negative infinity, y approaches positive infinity. And I said this whole like idea of this would be helpful later on. Well, this is where that comes in. The little arrow here meant x was getting closer and closer, well, in this case, infinity. So it's just heading off on the right side of the graph. Y is going to be heading up in the positive side of the graph. And as x goes to negative infinity, y is, going to negative infinity. I did not put that negative in there, did I? Let's see if I can fix that cleaner. Y is approaching negative infinity. Okay, so that's that same idea up here. So as x is approaching 0 right here, then what is the value of the function approaching? So what this question is really asking is it's saying, and I should probably have a question mark on here. So what it's really asking is, what is the limit? The limit is asking what y value does x get close to? I'm sorry, what y value does y get close to as x gets close to or approaches whatever number it is that you're looking at? In this case, we're looking at 0. So really, when I say the limit as x approaches 0, I'm really saying as x gets really close to 0, and really I should be coming from both directions. So as x gets really close to 0 from the left-hand side, and as x gets really close to 0 from the right-hand side. So we're not going off to the right side of the graph. We're not doing end behavior. We're getting close to a value. So as x gets really, really close to 0 on both sides, y is getting really, really close to a y value of -2. Actually, it's not even getting really, really close to it. It actually does get there. In this case, the point really is there. So, my destination is the location that I'm heading. Just like we are hoping for this corona results, where our destination is the place that we're heading. We would like to get back to normalcy. So in this case, that's what's happening. The destination when x is approaching 0 is the limit. So this limit would be equal to -2, because that is the y value that the graph is approaching as x is approaching 0. Next, I'm going to look at a piecewise defined function. So what if I had something like f of x equals 3x minus 2 for every value except for when x equals 0. But then when x does equal 0, let's say that that value is 4. Okay, so piecewise defined functions might not be your favorite, but they're just basically graphing it in pieces. So we'll still have that linear function that I had up here, 3x minus 2. The only difference is when x equals 0, we don't actually have a point there. So it's the linear function for every value except for at x equals 0, because of the fact that I'm making in the piecewise statement, we're only using 3x minus 2 when x doesn't equal 0. Then when x does equal 0, you are at a y value of 4. So if I asked you a question like, what is the value of f of 0? That's the question that says, when x equals 0, that's the destination. When x equals 0, what is the value for y? That's the question that's being asked. Well, that value would be 4, because when x is equal to 0, y does equal 4. I think he's jumping around for some reason. So when x does equal 0, y does equal 4. But if I bring in this calculus, which this is 100% calculus here, so when I bring in this calculus concept of a limit, limit is about motion and movement. It's about we're getting close to, so let's say I'm asking on the piecewise defined function f of x, I want x to just get close to 0. I don't care once we get to 0 what happens, I just want you to get close to 0. So again, you want x to get close to 0 from both the left side and from the right side. So if you want x to get close to 0 from both the left side and the right side, you have to recognize that my graph is getting, my y values are getting closer and closer to y values of -2. Even though there isn't a point there, that's okay. That is me knowing that I'm approaching that value. So limits are about approaching, not about what actually happens once you get there. I'm gonna make myself be a little bit bigger for a second here. Did that work? No, did this work? Oh, there we go. Okay. So just, I wanna make sure that you understand that this is about heading to a place. Even if there's no point there, I am heading to that spot. I guess I should go with your line. Which way is it? This way? I'm heading to that place where there's a hole in the graph because there's no point there technically, but that's still where we're going. So we are heading in the direction of being normal for, you know, COVID-19 and the economy, even if that doesn't ever actually happen, which it will. Let's say you are heading to school, all right, and something happens and your car breaks down and you don't actually make it. But you're heading to school. When you first got in your car and you were driving to school, your limit was equal to school because that's where you were heading. If you don't actually make it there, that's different. That's the destination. But we don't care about the destination when we're talking about a limit. We're talking about where you are heading to, where you're going. Okay. I can give you another. So these are all examples with graphs. I'll show you on a table in a second. So let's say we've got something like, I'll just go ahead and give you a picture. Okay, something like this. And then something like, let's just do this. I don't know what this could be. Just making it up. We'll say this is 1. We'll say that this value is, I don't know, 2. And maybe there's a point right here as well. Or no, maybe let's put this point at 1 just for a different number. Okay, so let's call this whole picture, whatever it is, we'll call this whole entire picture maybe a different, we'll call it g of x just for a different name. Okay, so this whole picture will be a graph of g of x. I'm going to ask you first, what is g of 1? That means when x does equal 1, what is the y coordinate? So when x does equal 1, the y coordinate is 2. Okay. The calculus question, so we'll say that's question 1 from this one. Question 2 could be, what is the limit of g of x, which means, remember, you can't take just limit equals. It has to be like, we wouldn't just say sine equals square root of 3 over 2. We'd have to say the sine of pi over 3 equals square root of 3 over 2. So it's the limit of g. I don't know if it helps to have me or not. It's the limit of g of x, which is this graph here, as x is approaching 1. What does that equal? So now we're back into, I want you to be heading to a location. I don't care about what happens once you get there. I want you to be heading to that value of 1 from x. So on both sides of x get really, really like infinitely close to 1, infinitely close to 1. As you get infinitely close to 1, my y values from both sides are getting infinitely close to a y value of 2, which is also the location. Like once you do get to 1, yes, there's a point there, but we are getting infinitely close to a y value of 2. I could ask you, what is g of negative 2? Again, this is an Algebra 1 question. This is when x does equal negative 2, what is the y coordinate? So when x does equal negative 2, the y coordinate, there's not there on the line part, but it's up there up above. So when x does equal negative 2, the y coordinate is a value of 1. The calculus question is, well, what happens as you move towards that point? So that's the limit question. So limit as x approaches negative 2 of g of x. So again, it's asking, what y value are you getting infinitely close to as x gets infinitely close to negative 2? So from both directions, as x gets infinitely close to negative 2, what y value am I getting infinitely close to from both directions? I'm getting infinitely close to a y value of 0. Okay? Let's look at this if we had like a table. So there's some things your calculator can do, which you probably didn't know. I love teaching you new things about your calculator. So one of the things that your calculator can do, which I know you already know, is it can do a table of values. So I could ask you, like, let's say I want to find the limit of x divided by the square root of x plus 1 minus 1. And so that's what I'm taking the limit of, so that would be my function. And I want to do it as x is approaching 0. So there's a couple things we can do. First thing I'm going to do, I'm going to minimize this way you can just see my calculator here. So first thing I'm going to do is pause the video so I can get my calculator. Okay, first thing I'm going to do is get my function that I'm finding the limit of. So that's over here again. So I'm going to take that limit, that function, which is x over the square root of x plus 1 minus 1, and I'm going to type that into my calculator, into y1. So that way I can look at this picture. So first thing I'm going to do is type this function into my calculator. Then, if you want, just in a standard window, we'll just start with that. In a standard window, so zoom 6, look at the graph, because that's what we were just doing. So as x is approaching 0 from both the left side and from the right side, you can see that the y values are getting closer to what looks like a value of 2. Okay? But I'm going to show you how to use the table feature on your calculator. So we're going to do this one by finding a table versus finding a graph, because the graph, sometimes when you're not really sure what's going on, it's not clear. And I can't just say, well, what happens at x equals 0? Because if I hit the trace button and I hit x equals 0, there's no point there. So actually there's a hole in the graph. And if you zoomed in enough, you would see that hole in the graph, depending on the pixels of your calculator. Sometimes you can see it, sometimes you can't, just depends. But there is a hole in the graph right there, which means there's no actual point there. So the destination did not get reached. You were on your way to school and your car broke down, you didn't actually make it. But in this case, there is no actual point there. But it looks like we're heading there from both the left and the right side. So from both left side and right side, looks like we're heading to that y value, but we don't actually get there. So I'm going to go to the table, and normally if I just hit second table, it has all these points already evaluated. I don't want to do that. I want to type in my own points. So go to right above window where it says table set. So you'll hit second window and change the independent variable, which is the x variable. Change that to ask. Basically what you're telling the calculator to do is, I want you to wait until I tell you what points I want you to plug in. You have to leave the dependent variable to auto, because if you change this to ask as well, it's not going to automatically spit out the y value. So I still want it to spit out the y value. I just want to tell it what x values to do. Now when I go back to the table should be empty, and it is. So now, like if I wanted to type in like that value at 0, you would see an error because we just said there's a hole in the graph there. We didn't have a point there, which means like on y equals, that just means I would have gotten 0 divided by, well, yeah, I get 0 in the denominator. Can't get 0 in the denominator. That's a problem. So there's no point there, but if we go to the table, we can still see there's no point. But I'm going to plug in points that are really, really close to 0 on the left side of the graph and on the right side of the graph. So like if I went to the right of 0, a number that's really close to 0, like 1. 1's pretty close to 0 on the right side, but it's not that close. You can get a number closer. You can get 0.5. You can still get closer. You can get 0.1. You could still get closer. You could get 0.01. You could still get closer. You could get 0.001. So you can get infinitely close to 0 without actually reaching it, according to, you know, math. But your calculator, if you go too far, like if I want 0.0001, sometimes the rounding gets so ridiculous. Your calculator jumps into scientific notation here, 1 times 10 to the negative 4th. And your calculator like basically gives up and says, okay, this is like 2.00000 something or other, but I'm giving up. I'm just going to round it to 2. But remember, 2's not actually there. There's a hole in the graph at that spot. So do understand that your calculator is sometimes a little misleading. But you can clearly see that, yeah, even at 1, it was, you know, a little more than, you know, a little less than 2.5. And at 0.5, it was pretty close to 2. But as I got even closer, like 0.1, and 0.01 and 0.001, you can see how much more clear it's obvious that I'm getting to a y value of 2. You also really technically should check the left-hand side as well. So if I go to the left of 0, like -1, I can obviously get closer. -0.5 is even closer. -0.1 is even closer. -0.01 is even closer. -0.001 is even closer. Oh, my calculator is switching into decimals, which is kind of a pain. If you want your calculator to be in, fractions. If you want your calculator to be in decimals, you have to go up to Y1, all the way up, hit enter, so your cursor jumps down here. Change this to a decimal, so you go math, change it to a decimal, hit enter, and then it'll change that number that was there into a decimal. Most calculators will have automatically done a decimal, but sometimes these color displays they like to be a little fancier. You can get even closer, -0.0001, but you'll find that if you go far enough, again, your calculator will give up and just say, I give up, it's 1.99999, so many nines, I'm just gonna go ahead and round it to 2. So here is me using the table showing, oh, I'm also getting to a limit of 2, which means that based off of the table and based off of the graph, I'm getting the same information. So I'm going to just make 2 notes of that. So based off of the graph, just drawing a quick sketch of it, the graph looked something like a hole in the graph here. And then no values less than -1, because -1 would cause negatives under the square root. So that's why we don't have any other points. So remember your domain of your square roots. And your graph would look something like this. So if I'm asking this question right here, I'm asking for x to get really close to 0 from both the left and the right side. Y values are clearly getting really close to 2. So the graph shows me that. Then if you use your table feature on your calculator, the table feature also told you that. So my table was values for x and y. And I was trying to get close to, I'm gonna put the 0 in the middle when I make my table here, just so you can kind of see what I'm doing with the left and the right hand side. So if I put the 0 in the middle here, clearly that value was undefined because we can't divide by 0, which meant there was no point there. But if I got close to 0 from the right hand side, 0.001, which was really close, was 2.005. 0.01 was 2.05. Nope, I had 2 zeros there. 2.005, 0.1 was 2.0488. That's enough that I can kind of see that one. Go to the left-hand side. So I had negative 0.001, and that was 1.9995. Then I had negative 0.01, and that was, maybe I didn't do negative 0.01. Let me just do it real quick. That was 1.995. And then negative 0.0 or negative 0.1 was 1.94, running out of room here, 1.9487. So then again, visually from the table, you can see, oh, here's X approaching 0 from the left. Here's X approaching 0 from the right. I don't really care what happens at 0. The point's not there. It doesn't really bother me. Y values are approaching a Y value of 2, even though that value isn't actually there on the graph. Okay? So I'm going to give you some practice on this, and that'll be good to go for this introduction video. Bye guys, miss you.